Hello. In the last class, we discussed about the particle nature of light. We also saw how using Rydberg's formula, we can discuss the emission spectrum of hydrogen atom. But we saw that Rydberg's formula was a nice construct which reproduced the emission spectrum of hydrogen atom, but it did not give us any physical insight. This was answered, or this physical insight was given by Niels Bohr, and this is what we are going to do today. We will learn about the physical interpretation behind the hydrogen atom emission spectrum that was given by Niels Bohr. Next, we are going to discuss Bohr's model. Niels Bohr, the famous Danish scientist, suggested a new model for the atom, which we call as Bohr's model. Before that, let us refresh our memory as to what we know so far. We know that up to now the most advanced model of atom was given by Rutherford. So, let us refresh our memory about Rutherford's atomic model. Rutherford suggested that every atom has a central core part, which is nucleus. Nucleus contains all the positively charged particles proton. It also contains the mass that is coming because of proton and neutron, and the electrons go around the nucleus in some circular paths. Now, electron is negatively charged, which is going around in circular path around the nucleus, which is positively charged. But Rutherford's atomic model had a problem. The problem is that Maxwell's theory suggested that if you have a charged particle and another charged particle is going around the former charged particle in a circular path, actually when a particle is going around a circular path, even if it is going into the fixed velocity, since at every point in this circular path it is changing its direction, this particle is said to be in constant acceleration. It is always changing the direction of its motion. So, therefore, it is under constant acceleration. So, when an accelerating charged particle goes around in a circular path around another charged particle, Maxwell's theory suggested that this particle should follow a spiral path, something like this, and in no time should collapse onto the other charge, which is around which this particle was orbiting. So, that means what? Rutherford's atomic model should have led to this situation where electron goes in a spiral path and collapses onto the nucleus. Therefore, the atom should not exist. So, Rutherford's atomic model could not explain the stability of atom. The stability of atom, the reason why the atom is stable, could not be described by Rutherford's atomic model. This we should keep it in mind when we discuss Bohr's model. All right. So, starting from this discussion, Bohr suggested that let us think about it. What is the problem? The problem here is that this electron which is going around this fixed path, it is emitting its energy, and therefore, it is undergoing this spiral path, and that it should collapse on the nucleus. So, Bohr suggested a few postulates through which we will study this atomic model. Postulates of Bohr. Bohr first suggested that the electron moves around the nucleus in what he called fixed paths. He called them orbits. These fixed paths have constant energy or a fixed value of energy, and he called them as stationary state. So, what Niels Bohr did was he said that this the electron goes around the nucleus in circular path, but these paths are fixed, they have a fixed radius, and they have the electron, as long as it goes around this circular path or the orbit, it has the same energy, it has a constant energy, and we call this state of electron as a stationary state. So, what Niels Bohr has proposed is something like this. He said that nucleus is at the center, the electron goes around the nucleus in concentric circles. So, there you can see there are many concentric circles. So, these are fixed orbits, each orbit has certain energy, and electron can choose to either stay in this orbit or in this orbit or in this orbit. So, but as long as the electron is in a particular orbit, it has a fixed energy, it has a constant energy, and since it has a constant energy, the collapse of electron onto the nucleus that was arising in Rutherford's atomic model disappeared, because of this definition that Niels Bohr postulated. Then again he said that all right, electron goes around the nucleus in a particular orbit, but it can also change its orbit. When it does so, he said that electron moves from one orbit to another or one stationary state to another. And how does the electron do that? It does that by absorbing or emitting radiation or emitting energy. So, he said that okay, electron, let us say electron is here, it can go to the next orbit. The next orbit will have he said that the higher orbits, the orbits farther from the nucleus will have higher and higher energy. So, if the electron is here, let us call the energy of this orbit as E1, the energy of this orbit let us call E2, and the energy of this orbit let us call E3. So, the electron can be in this orbit or this orbit or this orbit. If it is in this orbit, its energy is E1, if because that is the energy of the stationary state 1. The energy of the stationary state 2, we call it E2, and if the electron is in this orbit, its energy is E2. So, electron can move from this orbit to this orbit or this orbit to this orbit or even this orbit to this orbit, but it can do so by absorbing or emitting energy. So, if it is going from a lower energy to a higher energy stationary state, let us say from E1 to E2, it requires additional energy. So, therefore, it has to absorb energy from somewhere to go from E1 to E2, and if you want to come back from E2 to E1, it has got this extra energy which it can emit. So, and then it can come back to the lower energy orbit E1. All right. So, this is what he suggested in the second postulate. In the third postulate, he said that what is the value of this energy that it has the electron has to absorb or emit. So, let us say that the electron is going from 2 to 1 or second stationary state to the first stationary state. The first stationary state we also call that as the ground state. This is where the electron would like to stay unless you excite the system. So, 2 to 1, if we say the emission from stationary state 2 to stationary state 1, the energy difference between the two states are E2 minus E1, which let us call a fixed a number that is delta E. If this is the energy difference between the two states, so if the electron is coming from stationary state 2 to stationary state 1, this much energy it will emit. When it emits this much energy, we know that the energy has a equivalence with the radiation in terms of its frequency. This was given by Max Planck. So, he said that if there is an energy E, it is associated with a radiation, the radiation will have frequency nu. So, this is what Niels Bohr suggested, that if the electron is coming from E2 to E1, it will emit a radiation of frequency nu such that h nu is delta E. Right. So, if we know h nu, we can of course, if we know nu, which is now E2 minus E1 divided by h, that is delta E by h. We can also get lambda, which is nothing but c divided by nu, the frequency. So, we can write lambda h as h c divided by E 2 minus E 1. We can also use nu bar, because that is what we have been using. That can be written down as E 2 minus E 1 divided by h c. So, it does not matter, I mean we can express the radiations either in terms of its frequency, or in terms of its wavelength, or in terms of its wave number. These are the three postulates. There is one more postulate we will discuss next. We are discussing Bohrs model. Let us discuss the fourth postulate. Niels Bohr suggested the electron goes around this circular path with a certain with each orbit has a certain amount of energy E 1, E 2, E 3, but what is the value of this what is the value of the radius of these orbits? Can the electron choose any radius that it wants, or is there a restriction? Niels Bohr imposed a restriction on them. He suggested that only those orbits are allowed where angular momentum of the orbiting electron, which is given as mvr, is a constant. Or let us I am not let us discuss what this angular momentum is. If I have a particle of mass m and it is moving with a speed v, then I know that its momentum is given by p, momentum p is given by mass multiplied by its velocity. If the same particle, instead of going in a linear path, it goes in a circular path with around a circle with radius r, where its tangential, the particle's mass is m, the tangential velocity is v, then this particle which is going in this circular path has got an angular momentum, which is given as mvr. So, the mass of the particle, the tangential speed, and the radius of the circle around which the particle is moving. So, this is angular momentum that is given. So, Niels Bohr suggested that not all orbits are allowed, only those orbits are allowed which have certain value. We will come to the right hand side now. So, mvr, which is the angular momentum, has certain value. If you look at this right hand side terms, we have n. He suggested n can be 1, 2, 3 and so on, again numbers. H is the famous Planck constant, pi is a constant. So, we see that the angular momentum is essentially a constant, but this constant, the value of this constant depends on the value of n. So, mvr, the angular momentum of the orbiting electron, can either be h by 2 pi or 2h by 2 pi or 3h by 2 pi, or so on and so forth. So, Niels Bohr suggested that the electron cannot make any radius it wishes. It is restricted by the fact that it has to find a certain radius such that the small product of mass, velocity and the radius of that circle is either h by 2 pi, 2h by 2 pi, 3h by 2 pi. The angular momentum in the first stationary state or the ground stationary state is h by 2 pi, the second stationary state is 2h by 2 pi, the third stationary state is 3h by 2 pi. This is how the postulates of Bohr's atomic model were formulated. Starting from these postulates, Niels Bohr solved the problem of hydrogen atom. His essential assumption is that this the solution method that was adopted by Niels Bohr to solve hydrogen atom insisted that the system should have single electron. So, one electron. It can have many protons in the nucleus, but it should have maximum one electron, which is going around in the circular orbits. The four postulates of Bohr were starting from the postulates that Bohr formulated, the four postulates that we just discussed. Bohr solved the problem of hydrogen atom. The essential assumption in his solution was that that solution was applicable to any system which has got one electron. It could have any number of protons. So, it had one nucleus with certain charge, so certain number of protons around which one electron is orbiting. As long as this is given, the Bohr's atomic model could be used to solve the atomic spectrum of any other atom. Using this, we would now go through the results of Bohr's atomic model. We will not discuss how they were obtained, rather we will see the essential results that were coming out from Bohr's atomic model, and we will try to appreciate how these results could explain the very complicated hydrogen atom emission spectrum. Next, we discuss the results obtained from Bohr's atomic model. First key factor is that Niels Bohr assumed that there is a this is the Bohr's atomic model's picture. That first thing is that there are several orbits. The orbits, let us these are some ground rules. The orbits are numbered 1, 2, 3, so on and so forth. N goes from 1, 2, 3, 4. We will soon understand the physical significance of this n, but at the moment let us use it as a bookkeeping exercise, where n is an index which indicates the orbits 1, 2, 3 and so on. Using Bohr's atomic model, Bohr could find out what is the radius of any orbit. So, the expression that he got for radius of the f of any orbit, that was given by R n, he found it out as 0.529 multiplied by n square divided by z, and this is given in the unit of angstrom. If you look at this expression, you have a number 0.529. This number has the unit of angstrom, because the remaining term, this is n, which is the index here, it can be 1, 2, 3, just a number, and z is the atomic number of the nucleus. So, results from Bohr's model, these are applicable to all single electronic species. What are the single electronic species? Of course, one we know is hydrogen atom, that has got single electron, but who else can have single electron? Helium has 2 electrons, but if we ionize 1 electron, we remove 1 electron, then it becomes single electronic species He plus. We can take lithium and ionize 2 electrons, then that also becomes single electronic species. So, we can use Bohr's atomic model for hydrogen or helium plus or lithium 2 plus and so on and so forth. Only difference is that the Z value, the atomic number of hydrogen is 1, helium is 2, lithium is 3 and so on and so forth. So, we have to keep this in our mind. If we look at the expression for the radius of this orbit, we see that for hydrogen atom Z is 1. So, its essential is 0.529 multiplied by n square angstrom in the unit of angstrom. So, what is the radius of the first orbit? That is n is 1. So, therefore, the value is 0.529 angstrom. What is the value of R2? I will put n as n is 2. So, therefore, n square is 4, 4 multiplied by 0.529 angstrom, and that comes out to be 2.12 angstrom. What is the value of 3? Radius of third orbit? This comes out to be 4.76 angstrom if you use n as 3. So, n square is 9, 9 multiplied by 0.529. In this way, we can calculate the orbit of the radius of the Bohr's orbit for hydrogen atom. These are all for hydrogen atom, because we have used z as 1. If we use z as 2, then we will get the radius of the orbit for helium plus. Right. What is the final value of what is the maximum value of n? N can be anything, it can be as large as you want. But when n is very large, you see the radius goes as n square. So, therefore, the radius becomes infinite. So, therefore, Bohr's atomic model said that electron has, or electron can, if it chooses, if it can take that much of energy, then it can choose to go to a very high value of n. In that case, it will be extremely far away from the nucleus, as far as when r goes to the distance between them goes to infinite. All right. So, next we will discuss some more results from Bohr's atomic model. So, we saw that Bohr's atomic model could explain or could give analytical expression for the radius of these orbits. We can also use Bohr's atomic model to get the speed of electron in orbit n, in any orbit. This expression is given as V n, that the speed of the electron in the orbit n is 2.18 into 10 to the power 6 z divided by n meter per second. Again, z is a number, n is a number. So, they do not have any unit. So, the unit that we see here, meter per second, is coming from this term. If you want to convert this unit to any other unit of your choice, you can simply change this number in the new unit, and it works. We can write down the speed of the electron in the first orbit. If you see, for hydrogen atom, z is 1. So, for first orbit, n is again 1. So, the speed of electron in the first orbit is essentially 2.18 into 10 to the power 6 meter per second. Speed of the electron in the second orbit is when z is 1, because we are still in hydrogen atom, n is 2. So, it will you will get it at 1.09 into 10 to the power 6 meter per second, and so on and so forth. You can see V 3 0.72 into 10 to the power 6 meter per second. What you see here is that, first of all, the speed of electron is somewhat close to the speed of light. Speed of light is 3 into 10 to the power 8 meter per second. So, it is only 2 orders of magnitude less than the speed of light. So, it is quite high speed. But we also see that as we go farther and farther from the nucleus, the speed of this the speed of the electron keeps decreasing. We saw the radius of an orbit, we saw the speed of the electron in a given orbit. Next, we discuss the energy that we said E1, E2, E3, the energy of an electron when it is orbiting one particular orbit. Next is energy of orbit n or stationary state n. This is the Bohr's atomic model that we have. From Bohr's atomic model, the solution of Bohr's atomic model suggested that E n, the value of energy in the nth orbit, is minus 2.18 into 10 to the power minus 18 z square divided by n square, and this is given in the units of joules. You see this number, again z is a constant for hydrogen it is 1, n is a number which goes from 1 to 3, 4, so on and so forth. So, the unit that is coming here is coming because of this number. If you want to change this unit from joules to any other unit, you can play with this number. We discussed earlier that this is not a very convenient unit to deal with, because it always has 10 to the minus 18. So, I would convert it to the better unit, more convenient unit, that is electron volt. When I do that, I get this expression. And this is now in the units of electron volt, right. If you do a small exercise and find out the value of Rydberg's constant, we know that is 109677 centimeter inverse. Please convert this number to the units of joule or to the unit of electron volt, and you would see that this corresponds to 13.6 electron volt, this corresponds to 2.18 into 10 to the minus 18 joule. So, what we have now here as the solution for Bohr's atomic model, the energy for the in the Bohr's atomic model is essentially the Rydberg's constant multiplied by z square divided by n square. All right. We will write down the energy of few orbits. The first stationary state E1, its energy is given when I use n is 1, z is again 1 because it is hydrogen atom. So, the energy is minus 13.6 electron volt. The energy of the second stationary state is obtained when n is 2, z is again 1. So, this number comes out to be minus, so essentially minus 13.6 divided by 4 electron volt, which is minus 3.4 electron volt. E3, the energy of the third orbit is minus 13.6 divided by 9, which is minus 1.51 electron volt, and so on and so forth. If I go for a very large value of n is very large, in that case you see the energy decreases as n square. So, very soon when n is very large, E n goes to 0. One interesting thing that you would see is that the energy of these stationary states are all negative, and it approaches to 0 when n goes infinite, n tends to go to infinite. What does this negative energy mean? The negative energy means that electron, which is orbiting around the nucleus, is stabilized by the nucleus. So, the electron is happy in this nucleus, that is reflected by this negative value of energy, which refers to stability. So, the atom is stable, which is reflected by the fact that energy of the electron is coming out to be in negative numbers. So, minus 13.6 electron volt of energy in the stationary state means that if you want to bring out the electron from the first stationary state or the ground state of hydrogen atom, you must supply an energy of 13.6 electron volt. If the electron is in second stationary state, then you must supply the energy of 3.4 electron volt to bring out this energy. So, this energy that we are getting E1, E2, E3, they are essentially the binding energy of the electron to the nucleus. So, the electron is bound to the nucleus by an energy of 13.6 electron volt, and if you want to take it out, you must supply that much of energy. And the negative number, as I said, refers to the stability of the atom. And we see that as n goes higher and higher, n goes to very large number, then the energy goes to 0. And what does that mean? That means that when n is very large, if you remember the expression for Rn goes to infinity. That means the distance between the nucleus and electron is very high, and the energy of the electron is nearly 0. So, this is a state where we call it a free electron. So, the electron has completely escaped the field of nucleus and it is moving freely. It does not, it has no connection with the nucleus anymore, and we call that a free electron. So, the nucleus is called to be ionized, that the electron has completely left the sphere of influence of the nucleus. So far, we have discussed the postulates of Bohr's atomic model and the results of Bohr's atomic model. We saw from Bohr's atomic model, we could get an analytical expression for the radius of the different orbits. We could get an analytical expression of the velocity of the electron or the speed of the electron when it is in a particular orbit, and we also could get the energy of a given stationary state or an orbit. But we started with this fact that Bohr's atomic model was necessary to describe the hydrogen atom's emission spectrum. And now we will see that how Bohr's atomic model could explain the hydrogen atom's emission spectrum. So, we saw that the energy of the stationary state, nth stationary state, is given as RH, which is the Rydberg's constant, multiplied by z square divided by n square. For emission, we know that from Bohr's atomic model, if we are discussing an emission spectrum, so that means the electron is coming from a higher orbit, higher energy orbit to a lower energy orbit. So, let us say that electron is coming from n2 to n1, where n2 is greater than n1. In that case, the energy of n2, the higher energy orbit, is given as the energy of the stationary state to which the electron is going is given here. The difference in energy delta E, which is E n 2 minus E n 1, is given as I can rewrite this equation in the following manner. This is the delta E that we get, where n 2 is greater than n 1. If you remember the expression that Rydberg gave to explain the hydrogen atomic spectrum is now reproduced by Bohr's atomic model. Rydberg proposed that equation purely on the basis for the sake of explaining the numbers that were coming. However, Niels Bohr's atomic model could reproduce the same equation starting from a set of postulates, a set of fundamental rules, and therefore, thereby he developed a theory within which one can explain this the emission spectrum of hydrogen atom. This is what we will do next. Now, what I am showing you here is that the energy levels of different stationary states of Bohr's coming out from Bohr's atomic model. So, this is the ground stationary state. So, n is 1, n is 2, n is 3, n is 4, n is 5, and so on and so forth. Now, if I am talking about emission spectrum, so my electron is always in the excited state. So, the electron, if it is in state 2, then it can come down to 1, that is 1 emission. So, what will be the emission radiation coming out of this emission process? The radiation corresponding to the energy, that is minus 3.4 minus 13.6 electron volt. This energy difference corresponds to a particular frequency, and that will be the frequency of the light that comes out when the electron jumps from second orbit to first orbit. And if electron comes from third orbit to first orbit, it emits another radiation, and similarly we can go on doing this. So, in these 4 lines you will see that the initial state can be 2, 3, 4 or 5, but it is always coming down to the state n equals 1. This, if you calculate from these numbers, where is what we know as Lyman series. The similar way, we can also say that if electron is to begin with, electron was in the third state and it comes back to second state, or it could come from 4 to second state, or fifth state to second state, or sixth state to second state. These are all, these lines, they all represent Bohrs series. And similarly, now this is straightforward. So, if the emission is from 4 to 3 or 5 to 3 or 6 to 3 or so on and so forth, we call them Bohrs series. Right. So, this way Niels Bohr suggested that these are different energy levels. The electron can stay either in this energy level, this energy level, this or this or this, depending on how much of energy you have provided. If it wants to come from a higher energy level to a lower energy level, it emits radiation. This is what we do, and we are getting emission spectrum. And when if it wants to go from a lower energy level to higher energy level, it must absorb energy. That will give rise to the absorption spectrum. Now, since we are talking about this emission spectrum, you would see that you do not see emission line at every possible energy values. Actually, what you see emission is at certain energy values. For example, this line will come out minus 3.4 minus 13.6, this line will come out, the second line, this one will come out the energy minus 1.5 minus 13.6 electron volt, but in between these two numbers there will be no line. So, this explains why we get series of lines separated from each other in the hydrogen atoms emission spectrum. But then what happened? What about those bands that we are seeing? The bands come because you see as you go higher and higher in energy, these n equals 6, 7, 8 and 9 and 10, their energy level, they are very closely spaced. So, the emission that are coming from those energy levels to energy level 1 or energy level 2, they will all be closely spaced. They will have essentially same energy, emission energy. So, therefore, they will appear in the almost the same they will appear or they will give away the radiation of almost same wavelengths. This is how Niels Bohr with his simple atomic model could explain the very complicated features of the emission spectrum of hydrogen atom. We saw Bohr's atomic model could explain the emission spectrum of hydrogen atom, but there were several limitations to Bohr's atomic model. We will discuss the limitations now. The limitations of Bohr's model. One very important limitation is that this model is applicable only for single electronic species. You cannot use this Bohr's atomic model to describe the emission spectrum of helium atom or lithium atom or beryllium atom or any other atom. This is not possible. You can only do that either for hydrogen or helium plus or lithium plus 2 and so on and so forth. But nature is full of elements which are in their neutral state or which have more than one electron. So, Bohr's model could not explain multi-electronic species. That is a major limitation. The other limitation of Bohr's atomic model is that it could not explain the splitting of spectral line when the matter is under the influence of magnetic field or electric field. What was seen is that one could record the emission spectrum of a particular any atom in a normal condition, and then they got emission spectrum. But if you re-record this emission spectrum by subjecting the matter to under the influence of magnetic field or electric field, we saw that the spectral lines actually splitted. You got many additional lines in addition to the lines that we have already seen, and these were actually explained by Zeeman effect. They are known as Zeeman effect, or when under the influence of electric field they are called Stark effects. So, Bohr's atomic model could not explain Zeeman's effect or Stark effect. This is again another major limitation of Bohr's atomic model. The third limitation of Bohr's atomic model is that we wanted an atomic model which will not only describe the structure of an atom, which will also take us to describe the bonding in molecules, but Niels Bohr's atomic model could not describe chemical bond, and that was another major limitation of Bohr's atomic model. We will see how the limitations of Bohr's model could be overcome and what we can do to accurately describe the atomic structure of hydrogen and other heavier atoms. Before we could venture into the accurate description of atomic structure, we need to take a break and discuss a few other developments that were occurring in the field of science that changed our understanding of the matter forever. We will discuss two such major fundamental breakthroughs. One of them, the first one that we discuss, is what is known as de Broglie's hypothesis. De Broglie, it is written as Broglie, but he is a French scientist whose name is pronounced as de Broglie, and this D letter is written in small case. De Broglie, a young French physicist, in the year 1924 thought something very important. He said that alright, we have already established that light can have wave like nature or particle like nature. The duality of light or duality of radiation was established, because we saw that some features could not be explained by particle property of light and some other features could not be explained by the wave property of light. So, therefore, light is both wave and a particle. What de Broglie wanted to ask is that, well, if light or if radiation has both particle and wave like nature, which radiation we initially thought is a wave, then he asked this question that why can't particles, or any particle or any matter, have wave like nature? That was a big question. Now, wave had light as a wave, light had wave like nature and particle like nature. Now, de Broglie is suggesting that why not matter has both particle like nature and wave like nature. So far, we always thought that matter had a particle like nature. The electron or a cricket ball or the pen that we use, they all are particles. But de Broglie suggested that matter has a wave nature, or in other words, particle has a wave nature. All right. If it has a wave nature, then wave is usually characterized by its wavelength or frequency. Then what is its wavelength? He gave this relation. He said that the matter has a wave nature and this wave has a wavelength of lambda, which is given by h, the famous Planck's constant, divided by the momentum of that particle, momentum of that matter. What is momentum? We can again rewrite this as h divided by m v, where the m is the mass of the particle and v is the speed with which the particle is moving. And this was a very important hypothesis. When it was suggested as a hypothesis, because de Broglie could not provide a proof to his hypothesis, nor was there any experimental evidence, but later on we got some experimental evidence that matter actually has wave-like nature. We will come to that. But let us explore a bit more about this very puzzling statement that matter has a wave-like nature. That means, if it is extended, that it would also mean that you and me as massive bodies, or the pen that I am holding, or everyday objects that we see, they all have wave-like nature. So, if they have a wave-like nature, then where is the proof? But before giving that proof, let us first establish. Let us try to find out the wavelength of an electron which is in the first Bohr's orbit. What do we need to know for that? We need to know the mass of the electron, which is 9.1 into 10 to the power minus 31 kilogram, which is already known. The speed of the electron in the first orbit we discussed, 2.18 into 10 to the power 6 meter per second. If I know mass, I know velocity, then I actually know, using de Broglie's hypothesis, I can know what is the wavelength of this particle. So, lambda is given as h by mv. So, h I know, which is 6.626 into 10 to the power minus 34 joules second, divided by 9.1 into 10 to the power minus 31 kilogram, multiplied by 2.18 into 10 to the power 6 meter per second. If you solve this, you would get 0.33 nanometer. So, an electron, when it is orbiting the first Bohr's orbit or the ground state, it emits it has a wave-like nature, which is given as the wavelength of 0.33 nanometer. All right. But let us do another exercise. Let us say we have an object whose mass is 100 gram, and it is moving with a speed let us say 100 kilometer per hour. If I want to calculate the wavelength correspond for this particle, the de Broglie's wavelength for this particle, I have again the same equation h. So, 100 mass is 100 grams. So, I wrote it 0.1 kilogram, and the speed is 100 kilometer per hour, which is coming out to be about 27.5 meter per second. So, I am using all SI unit, and if you solve it, you would get this number. An everyday object with mass 100 gram has of course a wave-like nature, but its wavelength is 10 to the power minus 33 nanometer. So, you can see de Broglie's hypothesis, although it sounds very puzzling that how can matter have a wave-like nature, but it is all right, because for massive objects, for the everyday objects that we encounter, for them this wavelength is negligible. So, it is nearly a particle like it shows nearly particle like behavior, but microscopic objects like electrons, where mass is very small and their speed is quite high, in those cases the wave-like property of electron is very significant. De Broglie's hypothesis is not merely a theoretical construct, it has got major practical implications. Of course, when de Broglie proposed the hypothesis, there was no experimental evidence to support his idea, but later on there are experimental evidences available which suggest that matter actually has wave-like nature. For example, electrons have wave-like natures, they have been experimentally demonstrated and their wavelengths have been calculated and they match well with the de Broglie's relation. Using this concept that electron has wave-like nature, using this concept several equipments have been built. For example, the electron microscope, which is in modern science is routinely used to investigate very small object at molecular level, and these very interesting equipments are actually built on the fundamental concept that electrons have wave-like nature. Today, in today's class, we discussed one very important milestone in the history of science, that was de Broglie's hypothesis. We will continue our discussion and we will see another radical idea that changed the face of science forever, that will be Heisenberg's uncertainty principle, and this is what we are going to discuss in our next class. Thank you.